Just want to point out that on my key, I made a mistake here. I put a 4 down, but it should have been for number 11, should be x squared over 2. That's just power rule there. I think I was looking at this 4 here and I transferred that over. Any questions with any of these problems from page 1 and 2? Now, typically with a lot of these problems where, if you see a set of parentheses, usually that's a good indication that could be your potential U value. So I think the harder ones are where there's not an apparent parentheses in the problem. You have to either create it or do a little bit of guessing, trial and error to get to that U value. And then on the back page, you see bounds, but bounds is the last thing you do. You have to do your U substitution process first, take the antiderivative, bring your x back, and at the very end of the problem, then you can start plugging in your upper and lower bounds to get to your numeric answer. So today we're going to move into the other or exponential function, e to the x, but on the integral perspective. So this is page 3. So a little bit of recap from first semester. The derivative for e to the u is just e to the u times u prime. So we learned that first semester. But we also know that you only deal with that u prime if this is other than an x, right? We know that the derivative of e to the x is simply just e to the x because it's e to the x times 1. So because the derivative of the exponential function is basically itself, the antiderivative of e to the x is also itself. So the integral of e to the x is just e to the x plus c, but with u substitution, it's just e to the u du becomes e to the u plus c. So the derivative is just itself, and the antiderivative is also itself. So it would seemingly be an easy formula to remember, but for some reason, students struggle with this. I think maybe because it's just too easy. I think students feel like there has to be something that I have to do. So they start involving natural log or they start involving power rule. And it just doesn't seem correct when it literally is just itself. And so, I don't know, I feel like this is one where it's too easy. That's why students struggle with it. That's why I see mistakes that I'm surprised to see on tests or quizzes because this rule doesn't feel like it's correct. Okay, but we'll work on this and hopefully you'll be comfortable with this rule really is just working backwards from your derivative rule from first semester. Okay, so number one, we have e to the 3x plus 1 dx. We see that this fits with this e to the u rule as long as we have the exponent being the u value. So we're going to let the u value be the entire exponent. Oh, and here's something to keep in mind is that if you want to go through u substitution, that you want to make sure that your e is in the numerator. If your e is in the denominator, you need to move it up to the top before you assign your u value. So a couple of points to highlight is make sure if you want to use this rule that your e to the u is in the numerator. And the second is if you want to assign your u value with the exponent, make the entire exponent the u value. If you're looking at the exponent for the u value, you're never going to pick and choose a part of the u value, part of the exponent versus it's always going to be the entire exponent. So so it'll never be just a section of it. Okay, so just keep that in mind. So our u value is going to be the entire exponent here. So du dx is 3, cross multiply. Solve for dx. Integral of e to the u times du over 3. There is no x's to cancel out. That's a good sign. We should have to pull the 3 out. Notice that the 3 is in the denominator, so it needs to come out as 1/3. And now, if you look, this matches perfectly with the rule that we want to use. E to the u is simply just e to the u. We just have to hold on to our 1/3. And then our final step is if you're going through u substitution, you want to make sure you bring back your original variables. And again, as a reminder, because we're going backwards from first semester, that also means that imagine first semester, if we started with this, we should be able to get to a derivative of that. So we know the derivative of e to the u is e to the u times u prime. So 1/3 e to the 3x plus 1 times 3. The 3 and 1/3 will cancel out. We're back to this. So that's also something that you can kind of to keep in the back of your mind is that if you're unsure about what your answer is, see if you can find the derivative of your answer and see if that will bring you back to your starting point. Right. So, everything that you learned first semester, you should be able to go backwards from what we gathered at the end to the beginning, right? So now your answer is the original function, and then your starting point is the derivative. All right, number 2, cosine of x times e to the sine of x dx. There's a lot of variables going on here, but if we see that e to the sine of x, we at least want to consider maybe sine of x is the u value. And if we think about the derivative for sine, the derivative of sine is cosine, and we do see cosine elsewhere in the problem, so we should be able to be fairly certain that this should work out, right? Anytime you are considering what the u value is, think about the derivative. And if you see a version of the derivative somewhere else in the problem, that's a good sign that we should be able to, that we're going down the right path. So our u value here is the exponent sine of x. du dx, derivative of sine is cosine, cross multiply. Solve for dx. So now we're going to rewrite our problem here, keep everything that we did not underline. So keep the cosine x, the e, replace the sine of x with u, and replace dx with du over cosine of x. So we need the x's to go away, and they do. So now it's a very nice, clean, just e to the u. And our rule for e to the u is just e to the u plus c. No leftover coefficients to keep track of. And then bring back your x. And if we want to double check ourselves, we know the derivative of e to the u is e to the u times u prime. So e to the sine x becomes e to the sine x times cosine x. And that's what we have here. All right, example 3. Our u value, so first off, there's too many terms in the denominator. We can't just split up or do anything like that. So we're looking for u values. You may be thinking, what if the u value is just the x? Remember, we never want to do a one-for-one for u substitution, right? You're never going to have u being just x. Or maybe you're thinking the u value is e to the x. Then you have u over 2 plus u. But if you think about that, that's not large enough. We don't have a rule that can handle u over 2 plus u. So a bigger portion for us to consider is the entire denominator. It's easier to cancel something out in the numerator than it is for the denominator. So a lot of times your u value could just be the entire denominator. So in this case, if we think about the derivative for e to the x, it's just e to the x. We know 2 goes away. And there is an e to the x waiting for our derivative. So that's a good sign. All right, derivative, du dx. 2 goes away to 0, e to the x. Remember, e to the x is simply e to the x times 1, so it's just e to the x. Cross multiply. Okay, rewrite our problem. Keep the numerator. Denominator is u. Dx is du over e to the x. Our e to the x's cancel out. We're left with 1 over u du. We got a perfect match with the rule that we want to use. Now, this goes back to the previous section. So on the board there, I have rules that we eventually want to work towards memorizing for our quiz next week. So we know 1 over u du is natural log absolute value of u plus c. From yesterday. Then replace the u back in terms of x. So just to kind of give you some idea, on the AP exam, they say that all rules are fair game in terms of rules that we want to be prepared for. But in reality, the ones that not every rule shows up on the AP exam, but the ones that will show up for sure are power rule, e to the u, and 1 over u du. That's natural log. So those are the 3 big rules. Maybe, I guess, in addition to sine and cosine, those will show up as well. But these are the rules that we're working on in preparation for upcoming tests or quizzes. They don't show up as often, but sometimes they do show up. But if we talk about the big 3, it's power rule, e to u, and natural log, and integral and derivatives. So you're going to see them guaranteed to show up on the AP exam. So we are spending most of our time just working or using them and getting comfortable with them. Thanks, next page. All right, number 4, e to the x, cosine of e to the x dx. We do see a set of parentheses, so maybe that could be our u value. So let's target what's inside the parentheses. Now, I think what some students have questions about is, well, how come we let this be the u value and we don't let this be the u value? I mean, they're the same, so why not let these both be u values? Why do you think we want to just let this be the u value and leave this alone? What's the reasoning behind that? What's the derivative of e to the x? Just what? Just e to the x, right? So we want to save something for the derivative, right? We want to find a match for the derivative. If we let this be the u value as well, then we don't have anything saved for this to match and pair up with. Then you're left with an e to the x and the derivative that has no chance of canceling out. So sometimes it is a little bit of, I see 2 of the same things. I know that I want this to be the u value, but sometimes you have to kind of strategically choose what will be the better u value and what you want to save and leave alone for a future part of the problem. Okay. So here we want to let this be the u value in the hopes that this will turn into cosine of u, which we have a rule for, but we're saving this e to the x because we know we need to pair the derivative up with something because something needs to cancel out, right? Okay, cross multiply. All right, e to the x cancels out. So we're just left with integral of cosine of u. This is one of our original rules from the previous quiz. Not one of the new rules there. This is one of the previous rules. We know cosine's antiderivative is sine. So just sine of u plus c. And then replace the u back in terms of x. And if we think about going backwards and thinking about first semester, can we get from here to here using derivative? Sine of u becomes cosine of u times u prime. So cosine of e to the x times e to the x. And then we see that here. All right, number 5. You may be thinking that the 2x could be the u value, but that may be a little bit too small because then you're left with e to the u over e to the u plus 1. And we don't have a rule that has that complexity in terms of e to the u over e to the u plus 1. So we want the u value to be an even larger part of the problem. And what if we target the entire denominator? Okay, derivative for e to the u is e to the u times u prime. That's first semester rule, cross multiply. We make our substitutions. E to the 2x up top, denominator is u, dx becomes du over 2e to the 2x. We need the x's to cancel out, and they do, but there is a 2 in the denominator that we want to make sure we keep track of. Sorry, 1 over u du. So 1 over u is just natural log. Then replace the u back in terms of x. Number 6, same strategy as 5. If we just let u be x, that doesn't make sense. If we let the u value be just e to the x, that's still too many things going on. So again, target the denominator if there's not an obvious u value that's large enough for the problem. Okay, so try that. Let's see if we can both come across, arrive at the same answer here. Same strategy as above. Very similar setup as above. Now, when you find the derivative, one of them doesn't have a leftover term, but the other one does. E to the x is just e to the x times 1, but e to negative x is e to negative x times negative 1. That's going to force my sign in between to change to a minus there. Let's make our substitutions. Now, these are almost the same, but not quite the same. Remember, we can't cancel the cross addition or subtraction. Is there something that we can do to make these look more similar to each other? What can I do here? Yeah, take out the 2, right? What if I take out a factor of 2? That should then allow my remaining expression to match up a little bit more cleanly for me to get my denominator to pair up better, right? So the derivative did change that plus to a minus, and that's how we can be certain that we can get those to pair up nicely. There's a 2 left over, so 2 is in the numerator. We're left with 1 over u du. So natural log. Our u value is in e to the x plus e to the negative x. Any questions? Okay, so your homework is pages 3 to 4 in your homework packets. Let's go back and do some more test review. I'll send out a reminder this afternoon, and I'll also send you a link to a page where you can find these problems worked out. Let's look at page 3. We did page 2. Now let's look at page 3. So before we go and find values from across g of x or g prime or g double prime, let's build out our rules first. So we have a definition for g of x. That's great. We can use that, which involves the area. Let's go ahead and build g prime since we're going to need it. G prime is asking for the derivative of this expression, and that should remind you of second theorem. The second theorem says, because we're pairing two opposing operations, we just insert the upper bound into the variable. So this becomes f of x times the upper bound's derivative, so times 1. So basically g prime is just f of x. So that's one definition we can come back to. And now just find the derivative again, because elsewhere in the problem, we do see them asking about g double prime. So let's build g double prime. G double prime is just a derivative down from g prime. So we're also going to do the same thing on the right side, bring the f down one derivative down to f prime. So g and f are basically staggered relationship with each other. G is the antiderivative of f, which means that g prime is the f itself, which means that g double prime is the f prime. Okay, so now let's we know that a lot of the g functions are asking about the area that we see in these regions, and so we want to make sure that we are looking in the appropriate regions when we are looking at our diagram. So you're only going to look at what's between the graph and the x-axis, not other shapes that you see. So what I mean is we're only looking at these regions, even though you may see other shapes in your diagram. So it is common for students to start building out other shapes that they see. They may see a triangle here, they may see a triangle there, but those are not between the graph and the x-axis. So start off by shading very lightly so that you know that, so you don't get distracted by other shapes that may pop up from from what you see. So yeah, just make sure that you're only looking at what's between the graph and the x-axis. Anything else is not part of what we're looking at. So once you have those identified, then let's go ahead and represent the displacement for each of those regions. We know that below the x-axis, we'll have negative displacement. Above the x-axis, we'll have positive displacement. Circle is pi r squared, so therefore semicircle is 1/2 pi r squared. So 1/2 base times height, 1/2 2 times -1 is -1. This is 1/2 pi r squared. My radius of my semicircle is 2. 2 squared is 4. 4 over 2 is 2 pi. But I want to split 2 pi just into these quarter circles there. So negative pi and negative pi. 1/2 base times height. 1, 2, 3, 4. 4 times 2 is 8. 8 divided by 2 is 4. So I'm going to split 4 up into 2 triangles there, 2 and 2. All right, so part A, find g of 2. So g of 2, let's look at what the definition says. The definition says g of 2 means replacing the upper bound with 2. So definite integral from -2 to 2 of f of t dt. So then we're going to add up the regions that we see from -2 to 2. So just this semicircle, right? So -2 pi. Find g of -4. -2 to -4. That's what the definition says. Now, we're definitely looking at the region between -2 and -4, but what do you notice, especially if we're trying to read something off of a graph? The bounds, right? The bounds we would prefer to be what? Smaller to larger. Otherwise, we're reading backwards. And I mean, we can do it without changing it. Just have to know that if you're reading backwards, then below is positive and above is negative. So if you understand that, you don't have to do this. But I think it's more straightforward if we put the bounds and just understand. So then from -4 to -2, that's showing us -1. But if I want to negate -1, then 2 negatives makes positive. So +1. Next up, find g of 6. Let's go back. Let's go to our definition. G of 6 is the integral from -2 to 6. Add all these up, -2 pi plus 4. Next up, find g prime of 4. Let's look at our definition for g prime of 4. G prime of x is f of x, so g prime of 4 is f of 4. And now we're simply looking just for the order pair, right? This is the f graph that we see in front of us. This is the graph of f. So f of 4 is just what the y value that we see on the graph, 2. G prime of -2 is f of -2, and f of -2 is just 0. G double prime of 5, definition says, is f prime of 5. F prime of 5 is basically the slope of f. So at 5, my graph is here. I'm looking for the slope. This is a nice diagonal line. The slope of this line is just -1. For what values of x is g increasing? Justify your answer. So this is not the g graph. This is the g prime graph, right? Because this is the f, and f is g prime. So we're basically looking at the derivative graph of g. So let's label accordingly. Above is positive slope, below is negative slope. On the x-axis, slope 0. Let's find our x-intercepts first. And we're going to create a slope sine line for g. And then we'll be able to more appropriately answer it from our sine line. So our endpoints goes from -4 to 6. Our critical points are our x-intercepts, so -2, 2, and that's it, right? Just -2 and 2. We look at where our graph is located. Below means negative slope, above means positive slope. So below is negative slope. From -2 to 2, also below the x-axis, so also negative slope. And then from 2 to 6, above the x-axis, positive slope. So we can say our graph is increasing in this interval, right, from 2 to 6. And likewise, we can say decreasing in these two intervals because we see the down arrow, so that can be for part H. For part I, points of inflection. If you're looking at the derivative graph, points of inflections are the max and mins, the relative max, relative mins of your G prime graph. So in this case, the max and mins are at -2, 0, and 4. And then the positive and negative slopes just translates to concave up or concave down. So part I, we are creating our concavity second derivative sine line. -2, 0, and 4. Between -4 and -2, we see our G prime graph is rising. So that indicates that the original graph is going to have a concave up shape. So positive slope, negative slope, positive slope, negative slope. And because there's a change in signs at all three of these critical points, we can call each of them points of inflections. For part J, find the absolute extrema. So we're basically applying extreme value theorem. And extreme value theorem, you're testing endpoints and critical points. And you're only going to pick off your candidates from your G prime. Don't pick off anything from your G double prime. These are not candidates for max and mins. You're only going to pick off from your G prime sine line. So we definitely want to test -4 and 6. But do we need to test both -2 and 2? Which point do we not have to test? -2. Now, if you tested -2, it's fine. You won't lose any points. It's just that you're doing additional work that has no chance of being, being the absolute max or min. I did test it, but I didn't have to. But you only have to test your endpoints and your critical points and your valid critical points. And these points, I'm just pulling from the rule. But we also gathered these points from all the A, B, C's, and D's that we did above. So I'm just transferring those values down. 1, -6, and -2 pi plus 4. Pi is close to 3. 3 times -2 is -6. Plus 4 is around -2. So between -2, -6, and 1, my lowest y value is -6, or -2 pi. And my highest y value is 1. And then you don't have to specify the location, just have to tell me the y values. So I'm really looking just for these y values. Tell me what the highest and lowest y values are. Those are your absolute extrema. Questions? Okay, so tomorrow, I'll be checking pages 3 and 4. Help sessions tomorrow morning, 7:30, and Friday morning. The team go over this if you have any questions, but tomorrow in class, we'll do Riemann sums and we'll do a particle motion as well, just for additional practice. Okay. Okay, come get your phone.
Yeah. This is. We don't say it out. No, I was be that. You was the important question.
Particle motion. So let's just go from antiderivative from acceleration to velocity, antiderivative from velocity to position. Similar to the quiz. But instead of F prime, F double prime, I'm calling it acceleration and velocity.
Oh, yeah. I don't know.